All right. We are going to kick things off this morning by looking at one application of diodes um, and use it to develop what's called the small signal model for diodes. So let's start by analyzing the following circuit, where we are going to have some power supply voltage Vs. We're going to have a resistor here, which I'm going to call R bias. And then we're going to have a string of diodes connected in series. And I'm going to do 5 of them. Like so. All of these diodes will be identical so that they will all have a voltage drop of VD over them. They will all be carrying the same current, ID, and let's say that the sum of those 5 voltage drops, V out, in this case, is simply 5 VD. Our goal here is to determine the output voltage of our system under the constraint that our supply voltage is 10 volts and our diodes have a saturation current density of 10 times 10 to the negative 15 amps. So let's start. How do we analyze this guy? Any thoughts? We did analysis of diode circuits last Wednesday, I believe. Anybody got any thoughts at all? No. Okay. Well, what if we applied Kirchhoff's current law at that node? Said that the current that's flowing in is equal to the current flowing out. That seemed like a reasonable thing to do. Okay. So the current flowing in is simply Vs minus 5 VD. Oh, I guess I should have given you guys the value of my bias resistor too. I apologize for that. It's going to be 200 ohms. So we can say Vs minus 5 VD over 200 ohms, which is the current flowing into that node, is equal to my diode current, which is the current flowing out, where my diode current is IS EXP of VD divided by 26 millivolts. And you guys get your calculators out and tell me what VD and V out should be. Anybody get anything yet? Annabelle, you look like you're finished. So 748, I got 0.072 millivolts. All right. And then obviously 5 times that is V out. So that would be 3.74 volts. Okay. So before we get into talking about this guy, let me ask you a question. Was that analysis difficult? Okay. I'm going to expect you guys to be able to do it, here pretty soon. All right. So this circuit is what is called a voltage regulator circuit, okay? So what a voltage regulator circuit does is it provides an output voltage that is supposed to be independent of fluctuations in the power supply voltage, as well as independent of what load is connected to, okay? So what we're going to do is we're going to increase our supply voltage by 10% and see what change in the output we observe, okay? So if Vs is 11 volts, solve this guy again. All you guys using Casio, horrifying that you have to retype it. For people that are using a TI, you can literally just change one number and be done. 751.857 millivolts. And therefore V out changed up to 3.759 volts. So a 10% increase in the power supply voltage yielded a 0.5% increase in the output voltage, okay? So pretty stable. Let's see what happens if we make Vs 9 volts. Actually, when you get something, just shout it out. $743.655 millivolts, which makes V out 3.718 volts. So VD changed by negative 4.417 millivolts. V out changed by negative 22 millivolts. And so this is a 0.6% change. So again, we see the 10% change in the power supply voltage yields a pretty small change in the output voltage. All right, so the last thing I want to do here is rework this problem, but with a resistor connected across the terminals, right? So we go from a load resistance of infinitely large to some finite value. Let's call it a 1 kilo ohm resistor. So how is that going to change our equation? Let's start there. Anybody got any thoughts? It's obviously no longer going to be just this because there's another resistor in, right? Race. What do we do to fix this equation? Sure. So this is the current flowing in. That bit doesn't change at all, right? But our current flowing out of the node is now going to be the diode current plus V out over 1 kilo ohm, or 5 VD over 1 kilo ohm, right? What'd you get?
I got 0.739. So 739 volts.
That is not what I got, but it's, I mean, it's reasonably close. Anybody else get something? Yeah, I got 744.854, which changed our output voltage to 3.724. So there was a change in VD of negative 3.218 millivolts, and there was a change in V out of negative 16 millivolts. So overall, we had a 0.4% change. So as we make this load resistance smaller and smaller and smaller, we'll actually find out that this change in V out is going to get larger and larger and larger. And it's because that load is effectively stealing current away from that chain of diodes, which is then pushing those voltages lower and lower and lower, right? So as long as our load resistance is fairly large, this is going to work okay. But as we start making that load resistor smaller, we don't get, we start messing with the efficiency of our voltage regulator. But hopefully we all can see, this is a pretty stable system, right? While the analysis that we had to do here wasn't particularly difficult per se, it was rather tedious to have to repeat over and over and over again to see what those changes to the system would do to the operating point, okay? So in order to avoid having to do these tedious calculations, we are going to develop a small signal model, okay? So effectively, if we have a circuit like this, where this is our voltage, VD, and this is our current, ID, we want to develop a model that can handle something like this. So this current will now be ID plus delta ID, and this voltage drop would be VD plus delta VD. That's our goal. And this kind of gives away what we're going to wind up doing, hopefully, which is to be able to perform our analysis using superposition. Okay, so we can do some large signal analysis to establish the operating point of the circuit, here characterized on the left by the quantity ID, the diode current, and VD, the diode voltage. And then we're going to superimpose on top of that some small signal perturbation, which gives rise to a change in the diode current, delta ID, and a change in the diode voltage, delta VD. Okay, so the key to developing this model is understanding what's going on at the characteristic curve level for our diode, right? So if we have a forward bias diode, here is ID, here is VD. Our characteristic curve looks something like this, right? I'm going to call this point the Q point. Q stands for quiescent operating point. So effectively, this is where our circuit is DC biased, okay? And so this biasing point has a corresponding value of VD and a corresponding current, ID. About this point, we could draw a tangent line where if I could draw, this would be straight. Try again. Oops. So based on what we saw with the example problem that we worked, if we perturb the system by a small amount, we're really just moving this quiescent operating point either a little up or a little down the curve. And if that change is small enough, it's effectively linear, okay? So even though we have an exponential response overall from a large signal perspective, from a small signal perspective, this guy looks fairly linear. And the slope of our tangent line is 1 over RD. Where RD is what I'm going to call the dynamic resistance, okay? It is a dynamic resistance because it obviously changes depending on what our operating point is at, right? Because it's the slope of that tangent line, but if we were somewhere down here, that slope would be appreciably different than when we're operating up here, okay? What we're going to do now, we're going to derive that guy. And it's not particularly difficult, although for whatever reason, the textbook I have chosen doesn't do it. So the partial derivative of the diode current with respect to our diode voltage VD is nothing more than the partial with respect to VD of IS EXP VD over VT minus IS. Where if I put a parentheses here, that's where the extra term of IS is coming from the fact that it's usually IS times blah, blah, blah minus 1. And I'm just moving that IS to the outside there. So that when we take a derivative, it's obvious that part's going to go to 0, right? So that's going to leave us with let's see. So when we take the derivative of this guy with respect to VD, that's going to pull out a factor of 1 over VT, right? So that we're going to have IS over VT, EXP of VD over VT, which is effectively, so IS EXP of VD over VT is very, very close to ID, right? Because we just need to subtract that very, very small reverse saturation current from it. And so this gives us ID over VT, which is 1 over RD. And so from this, our dynamic resistance, RD, is simply the thermal voltage, VT, divided by the large signal diode current, ID, okay? So the dynamic resistance, RD, depends on what amount of current our diode is currently carrying. Sorry, Abdul, I don't know how to move the podium enough for you to see what I wrote in the corner. Okay. So I cannot emphasize this enough. This is not the resistance that we would see if we took a diode and hooked it up to a multimeter and tried to measure resistance, okay? This is dependent on where this guy is biased, right? So let's take this concept of a dynamic resistance and use it to rework the circuit that we opened class with, okay? So we had this guy here. Here is our bias resistor of 200 ohms. We have our string of diodes. Minus out. Voltage drop over any individual diode was VD. The current flowing through the chain of diodes was ID. We know that R bias 200 ohms. VS was 10 volts. Bless you. IS was 10 times 10 to the minus 15 amps. And we found that VD, using Kirchhoff's current law, we found that VS minus 5 VD divided by our bias was equal to IS EXP VD over 26 millivolts. And we were able to solve this guy and find that VD, and I'm going to call this VD comma Q. So this is our diode voltage at our DC operating point, 748.072 millivolts is what I got. I believe that's pretty close to what Annabelle got. So from this, how do we get our DC operating current? Anybody? Literally already on the board. You just got to tell me which part to use. Yeah, this bit. Plug it in right here, we're good to go. Or plug it in right there, we're also good to go. They're equal to each other, so it doesn't particularly matter, right? So if we sub in our known value for VD into this side or that side, actually, we'll wind up finding out what our diode current is, which in this case, I got to be 31.298 milliamps. And therefore, my dynamic resistance RD is simply 26 millivolts over IDQ, or 0.831 ohms. Okay. So if we want to employ the use of our small signal model, we first have to analyze the circuit at a constant DC level. Okay, that is our first step. Analyze the circuit to get the operating point, either using our exponential model, or if we were doing this as part of a design problem where we were just bought some silicon diodes or something like that, we could say, all right, so I know that the VD on for a silicon diode should be somewhere around 0.7, so I could use that voltage of 0.7 volts to solve for what I believe IDQ to roughly be, and use that as a starting place for our dynamic resistance, right? So either using our exponential model or our constant voltage drop model, we need to determine what our dynamic resistance is. Now we get to analyze the circuit at a small signal level, okay? Which means there are not going to be any diodes in our circuit anymore. All of our diodes are going to be replaced by that dynamic resistance. Since we have linearized the circuit, we can use any circuit analysis technique that we've developed in any of our 221, 223, 224 classes and all that kind of stuff, and they're fair games because we're now behaving linearly, okay? So if I asked you guys, so what change in output voltage occurs if Vs changes by plus or minus 1 volt, we would analyze that by looking at the following circuit. So my source now is just going to be the peak value of my change. I have my bias resistor. I have 5 dynamic resistances in series, so I'm just going to call that 5 RD. I'm going to call this at the output delta V out. Okay. So this is what's happening at the small signal level, which is superimposed on top of my large signal DC operating point, okay? So if I wanted to get that change in the output voltage, how would I do it? Voltage division, absolutely right, okay? So that's going to look like 1 volt times 5 RD over R bias plus 5 RD. If we plug in our values, we get 20.345 millivolts. So when the power supply voltage increases by 1 volt, we should see that our output voltage increases by 20 millivolts. If our power supply voltage decreases by 1 volt, we should see that our output voltage decreases by 20 millivolts. Let's compare that to our exponential model analysis that we did earlier. All right, so I'm going to scroll up here real quick. So the change in V out when the power supply voltage increased was 19 millivolts. The change in V out when the power supply voltage decreased by 1 volt was 22 millivolts. So that's a pretty good approximation with significantly easier work, not having to solve weird system involving exponentials and all that kind of good stuff, right? So we get something pretty dang close without a whole heck of a lot of effort involved. Now, if we want to figure out what change in the output occurs if we include a load resistor, we have to we can still use the dynamic resistance, but we have to think about what's happening, right? Okay. So what I mean by that, let me scroll up here real quick. I went to, no, there we go. So if we put that resistor our load resistor of 1 kilo ohm right here. Let's call this IR, okay? So nominally, what do we expect that resistor current IR to be? A reasonable estimate, okay, would be 5 VD divided by 1 kilo ohm, right? So we're saying if it doesn't cause a change or anything, that would be a good starting point estimation, okay? If the resistor current is 5 VD over 1 kilo ohm, then that means our diode current is going to decrease by that same amount because the current flowing into the node has to stay constant, right? So KCL tells us what's going on there. So if we were trying to answer the question, what change in output voltage occurs if RL is equal to 1 kilo ohm, IR would be 3.740 volts divided by 1 kilo ohm is 3.740 amps. Well, that's pretty straightforward. And then our change in V out would be the change in our diode current, negative 3.740 milliamps times our dynamic resistance, which in this case gives us negative 15.534 millivolts. Does that operation make sense there? Okay. So we're saying that that load resistor is stealing current away from our chain of diodes. So the change in the voltage drop should be how much current was stolen multiplied by the dynamic resistance of all of our diodes. Not, hopefully nothing too wild or crazy there. How does this compare to our original analysis? When we put a 1 kilo ohm resistor in, we saw that the output voltage dropped by 16 millivolts. Using our dynamic resistance, we saw that the output voltage dropped by negative 15.5 millivolts. So it's still a very good approximation. This dynamic resistance approximation is valid if the change in VD is around 5 millivolts or less. Okay. So if the change in a single VD is 5 millivolts or less, this is a good approximation. Anything beyond that, and it starts to get a little bit questionable. And it's because the shape of our exponential may have changed significantly in that swing. Okay. All right, so how do you guys feel about our small signal model for diodes? I think it's a fantastic tool, okay? Because one of the biggest reasons that I like the small signal model is it linearizes our circuit so that we can use simple circuit analysis techniques. We are going to find in this class that we are going to have small signal models out the wazoo. When we get to transistors, we're going to have small signal models for our BJTs, a couple of them. When we get to MOSFET transistors, we're also going to have multiple small signal models. And it's going to make understanding how these devices work as portions of amplifiers and all that kind of good stuff so much easier to understand than having to deal with our crazy exponential models and all that kind of stuff for everything. Okay. All right, so we have talked about large signal diode models, our Shockley or exponential diode model, our ideal diode model, and the constant voltage drop diode model. We've now developed a small signal model that we can use for perturbations in the system or small changes to things to see how our system behaves. So it's time to start talking about diode applications. Okay. We've obviously already covered voltage regulators, which let me scroll up here real quick. This was an example of a voltage regulator. In practice, it would be much more likely for us to see a well-defined Zener diode in a reverse bias configuration than 5 normal diodes in a forward bias configuration. Nothing inherently wrong with this. It's just a Zener diode does the same job with only a single component. We just have to make sure that it's giving us the right voltage. Okay, so anyway, I say that to say that as you guys work on, senior design projects and things like that, some of you might wind up needing a voltage regulator, and you may decide to design your own. Zener is a little bit more stable than this, but this would work. All right, so the next type of diode application that I want to talk about is what are called limiter circuits, okay? And I think this is going to be the last bit that we're going to talk about today. So to start with, a limiter circuit is a subset of what are called clipper circuits, okay? Clipper circuit is a very generic term. All a clipper circuit does is clip off part of a waveform, okay? Limiter circuits are used in wave shaping applications, so what I mean by a wave shaping application is simple diode limiters are part of the output stage of a huge number of guitar effects pedals, actually. We'll kind of find out why in a minute, but they introduce a very specific type of distortion because of what they do to the input signal. They're used in wave shaping applications, and they're also used in protection circuitry. So effectively, every pin on an integrated circuit chip, like an op amp or something like that, actually has one of these limiter circuits before you get to the actual circuitry inside the chip. It's called a form of electrostatic discharge protection. And so all that means is that if enough static electricity were to build up without that, you could fry everything inside it. There's a simple diode and resistor combination connected to every single pin before your vias and all that kind of stuff get to the bolt to where it just blocks any large voltages from hitting the sensitive bits. Okay? So the two most simple form of limiter circuits are these guys. We have a resistor R in series with a diode. Our input voltage Vin is applied on this side. Our output voltage V out is taken here. This is what's called a positive clipper. And if we replicate this circuit, but change the orientation of the diode, we get a negative clipper. All right. So let's analyze the behavior of our positive clipper circuit first, and we're going to use the constant voltage drop model. All right. So when Vn is less than Vd on, our circuit looks like this guy, right? So when Vn is less than Vd on, that means our diode is reverse biased or forward biased. You got a 50-50 shot if you're just blindly guessing. Vn less than Vd on, come on. What? Reverse biased, okay. So using the constant voltage drop model, what does a reverse bias diode look like? An open circuit. So our diode current is obviously 0 amps. What does that make happen to our output voltage, right? So under reverse bias conditions, what should our output voltage here be? Input voltage, exactly right. So V out should be equal to V in. When V in is greater than Vd on, our circuit will look like this guy, right? So for a forward biased diode, using the constant voltage drop model, we replace it with a battery. So our diode current now should be non-zero. Our output voltage will be what? Right, VD on. It's pinned to that effectively. So we can describe the input-output relationship of such a circuit in a couple of different ways. And so I'm going to try to draw out both ways real quick. Okay. So one way that we can do it, we'll plot. This is VD. Sorry, that's VN. My apologies. This guy is V out. And let's say that this voltage here represents VD on. So our relationship should look something like this. Constant value after VD on, and something like that before VD on. What should our slope be? What's the slope of the diagonal line going to be? 1. Because the output voltage follows the input voltage. So if we had a sinusoidally varying input waveform, oops. I'm not entirely sure I understand what you mean by look like a square. Exactly right. It's going to be clipped off. So this guy cuts off a large portion of that positive half cycle, just depending on how Vn compares to what Vd on is. So let me scroll up here real quick. What do you think the negative clipper circuit is going to do? The exact opposite thing. All of the positive half cycle is going to get passed, but it's going to clip off a portion of the negative half cycle. So anything that's more negative than negative VD on gets cut out. Right? So for a silicon diode, this is effectively a way of making sure that the positive, the voltage that's getting applied to some circuitry downstream never gets larger than 0.7 volts or potentially more negative than 0.7 volts. And we can actually put both of these guys in parallel and make sure that the voltage that's applied is always going to be between positive 0.7 and negative 0.7 if we wanted to. So that would be what's called symmetrical clipping. We can also do asymmetrical clipping by putting different types of diodes in, which is a practice that's done a whole heck of a lot in the design of effects pedals for guitars. We can make all kinds of funky wave shaping things by putting like a green LED for one diode and a red LED for the other, because they have different VD on values. They offer us asymmetrical clipping, which gives us a different sound than you would get if you just use symmetrical clipping or a pair of 1N 4008 diodes or whatever. Okay. Sometimes though, we want to have the portion of the waveform cut off be significantly larger than the VD on for our diode. So what do you think we could do to modify this guy to give us a higher range before the clipping occurs? Nope. Also no. We had a voltage source. So we can make it a biased clipping circuit if we put a bias voltage V bias here, or alternatively, for a negative clipping circuit, we would change the polarity of our biasing voltage. Okay. So what is that going to do to our model? Effectively, yeah, it just makes the value of VD on seem much bigger because it's added in series to that bias voltage. Okay. So when when VN is less than VD on, when we're in the reverse bias condition, it behaves exactly the same. But when we're in the forward bias condition, it's just giving us something like this, where we're still going to be going up, but now the clipping occurs up here instead of that low value of VD on, where this would be V bias plus VD on. These bias clipping circuits are used a lot to eliminate noise. So spurious signals that are going to be superimposed on top of something that we want. So this is a way for us to limit effectively like an inrush signal where we expect things to normally be at a level of around, let's say 10 volts, but noise could push it up to 12. Well, this keeps everything 10 or less, which is safe for the operating point of the system. Okay. So these are our limiter circuits, all right? What if, we're gonna talk about just one quick example here, and then I'll let you guys get out of here. We changed the order that we apply these elements, all right? So what if we had, dang it keeps going crazy on me. I'll do it down here. We had a diode, and then a resistor. Plus minus V in, plus minus V out. And then we could obviously also do the same thing where we just change the direction of the diode. Okay. So the one on the left is going to be the positive blah, blah, blah. The one on the right is going to be the negative blah, blah, blah. And we'll give it a name here in a minute. Okay. So how do we expect these guys to behave? Exactly right. So these are what are called rectifier circuits. Okay. This is a positive rectifier. This is a negative rectifier. So we analyze the positive rectifier circuit. When VN is greater than VD on, V out is nothing more than VN minus VD on. And when VN is less than VD on, Haley, what's V out going to be when VN is less than VD on? Let me ask you a question. Is that resistor R part of a closed current carrying loop? Shaking your head no, you're correct. So if the resistor R is not part of a closed current carrying loop, how much current flows through the resistor R? None. If there's no current flowing through the resistor R, then what's the voltage drop over the resistor R? 0. So the output voltage is 0 volts. So this is V out, this is V in, this is VD on. Our transfer function, or whatever you want to call it, is going to look something like this. It's going to be flat until this happens and we have a slope of 1. And so I'm going to draw the input and the output voltages on the same graph. Sorry, this is T. This is V of T. So for an input voltage that looks like this, our output voltage is going to look something like this. Where the peak value of this guy is whatever VN's maximum value is, and the peak value of our output is just VN peak minus VD on. Okay. We'll get into much more numerical analysis about what I'm about to talk about next when we return from the break. But I just want to ask you guys a simple question. What would happen if I put a capacitor C in parallel with that resistor R? Pardon? Well, it depends on what the value of C is, but sure. So effectively, that capacitor is going to charge, and it's going to take time for it to discharge, right? So depending on the value of the capacitor C, we could see something as simple as it going down like this. So it just drops off, or it could come over here like this if it takes a really long time for it to discharge. If we make it so that our input signal, the frequency of our input signal is, let's see, trying to think how to explain this correctly. So if we make it to where the time constant of that RC combination is much, much greater than the period of our input signal, we effectively never give the capacitor time to discharge, which is going to make the output look like a straight horizontal line. So a rectifier circuit there with that filter is how we convert an AC signal into a DC signal. Every single one of your laptop chargers has one of these. Actually, it has something slightly different. This is an example of what's called a half-wave rectifier because it's only rectifying the positive half of the wave. It's cutting off the negative half. Okay. We'll talk about a full-wave rectifier when we come back from the break, where a full-wave rectifier effectively flips the negative half cycle to positive so that we can use a smaller capacitor to get that DC output. So some of you are nodding your heads. Maybe you just figured out how to do your design problem, something like that. I don't know. Okay. Well. All right. So I think that's enough out of me for today. So I hope you guys have a good and safe holiday break. I will see you when we return on January the 5th.